Okay, we're continuing on chapter 4, I believe. Been a little bit since we've lectured, but last time we got into something, atomic number, I think. So remember the atomic numbers are number of protons there are in an atom. We also talked about mass number, which is our number of protons plus our number of neutrons. Remember, you can use both of these and subtract them, and that will get you your number of neutrons. We do typically write our isotope sort of symbol, and top left of it there is our mass number. Bottom left there is our atomic number. And remember that it is only the atomic number that can be found on the periodic table, and that is the top number there. Again, a reminder that the bottom number on the periodic table is not the mass number, it is the atomic mass. So do not use that as the mass number. The atomic number, mass number, protons, electrons, neutrons, they all should be positive whole numbers. And you should have a way to calculate all that. Once again, bottom number, not the mass number on the periodic table. Speaking of the periodic table, we talked about the periodic table as well. And we talked about group numbers, which is 1, 2. We skipped the middle, 3, 4, 5, 6, 7, and 8. Usually like a staircase kind of happening in that region. And to the left there of the staircase are metals. Kind of to the upper right of the staircase are nonmetals. And right on sort of that staircase that kind of comes down where boron is and down are what are known as metalloids, are semi-metals. We also talked about periods. Periods go left to right on the periodic table. Remember that group 1 starts with lithium, not hydrogen, even though hydrogen's over there. Hydrogen is not a member of group 1, and that's because ultimately hydrogen is a non-metal. So even though it's over on that side, it is a non-metal. Group 1 is the alkali metals. Group 2 is the alkaline earth metals. Group 7 is our halogens. And group 8 is our noble gases, right? So again, you do know those groups, the group numbering, where things are found. Transition metals are found between group 2 and group 3. So between group 2 and group 3, that area is our transition metals. And the two bottom rows there are lanthanides and actinide series, which again go right about there in the transition metal region. Again, this is the only place I've ever seen periodic tables where they put them kind of in the right spot. Those are the two rows. They're typically on the bottom, the periodic table. As you can see, it makes the periodic table quite wide. Thank you. If you put it sort of in the right location. Any questions on any of that stuff we talked about there? Okay. Then let's continue on with this chapter here. We kind of talked about the noble gases there, I think. So let's continue through that there. Something else we touched upon when we were talking about the periodic table last time is diatomic molecules. Diatomic molecules are molecules that are basically made up of only two atoms. There's a number of elements that come as diatomic molecules. Oxygen, nitrogen, there are examples, but hydrogen, oxygen, nitrogen, fluorine, chlorine, bromine, and iodide. These all come as diatomic molecules, and they're all still elements. A molecule, right, is just two or more atoms together. But a reminder as well that if it is a diatomic molecule, that's basically just referring to the fact that it has two atoms. It doesn't necessarily mean that it has to be two of the same. These are all elements, but you could have something like CO, which is carbon monoxide, and that's carbon atom and oxygen atom. Let me make it a little bigger there. Oxygen atom. And that is a diatomic molecule as well. That is not an element, that is a compound because it's atoms of two different elements together. So that's really important as well. And there's some of the characteristics there of our elements. Let's talk a little bit about solids. Some solid non-metal elements have a varied sort of structure than metals. They differ than elements in their sort of different forms. So different forms of the element are called allotropes. Carbon's an example of that. Depending on sort of how carbon's put together, it may be a diamond, it may be like pencil lead and graphite, or it can be a fullerene, which is basically 60 or more carbons together in a soccer ball sort of situation that's occurring. And here's the deal. These are all carbon atoms, but in diamonds, they are arranged a little bit different than they are in graphite. In graphite, they're kind of put together more in sheets and also cost more. Diamond versus graphite arrangement of carbon in that particular case. And like I said before, fullerenes are basically 60 or so carbons all arranged. Has sort of a soccer ball sort of shape to it. So let's officially talk a little bit about ions, and we'll talk more about it in a later chapter. But I think we might have touched upon it when we are doing our protons, electrons, and neutrons. Ions are things that have charges, and as we will talk about here, there are basically two types of ions that we come across. There are cations, which are positively charged, and there are anions, which are negatively charged, guys. So anything with a charge is known as an ion. And like I said, if it's a positively charged guy, cation, a negative charge, anion. Now, when we look at an ion, for example, if we take sodium, take a look at it here. So if we take sodium just from the periodic table and we kind of look at sodium's little arrangement there, sodium is number 11 on the periodic table. And if we have a neutral sodium atom, we know it's neutral because there's really nothing written right there. That is typically where we see a charge written. We know from its atomic number that it is 11 and that has basically 11 protons, which means it has 11 positive things. As we know, protons are positively charged in an atom, electrons are negatively charged in an atom, and neutrons have no charge. So they really don't come into play at all, neutrons, obviously, since they do not have a charge, they can't affect the charge of the overall thing. In a neutral one, we would need a matching number of electrons, which would be 11 in this case. And that really is what gives us our no charge that we see here. Something like sodium typically will make a +1 charge. Now, when sodium has a +1 charge, we know from our conversation earlier that it is the protons that is the most important subatomic particle. That is the one that determines what element we're dealing with. Again, if you look at the periodic table, every element has a different atomic number, which means every element has a different number of protons. So obviously we cannot change the protons, otherwise it would no longer be sodium. So protons are pretty much locked into place, and obviously because of its atomic number will still be 11. So neutrons again have no effect on it because they have no charge. So that really just leaves electrons as what affects the charge of something. And in this particular case, it would actually be 10 electrons. So if you have 11 positive things and 10 negative things, that leaves you a +1 left over. And once again, that is where the charge comes from. it is number of electrons change. We could represent this by looking at the difference here, and the difference between the neutral sodium and the sodium with a +1 charge is the number of electrons, and the one with a +1 charge actually has one less electron than the neutral guy. And because it is a positive charge, that is a cation. So that is a cation that is positively charged, and a cation results from losing electrons. So when you lose electrons, you become more positive, and you become more positive because now you have more protons than you do electrons in that atom, and it will get an overall positive charge that's going to happen. That is what the plus symbol means. So if you see something with a plus charge, it has lost electrons from its neutral atom. The actual number of the charge will tell you how many electrons. So like we see here with a +1 charge, it has lost one electron from the neutral atom. We could represent this with a little equation, starting with our sodium. Going to form sodium with a +1 charge and giving off an electron. Electron here on the product side of the equation represents that it is being lost or given off. And that is the way we could represent sort of the loss of electrons in this particular case. A cation like magnesium, if we take a look at magnesium on the periodic table, it is number 12. And if we had a neutral magnesium, it would have 12 protons, which are positively charged. It would have to have a matching number of electrons to give it no charge. And once again, that's why there is no charge basically written there. Magnesium typically forms a +2 charge. So when magnesium forms a +2 charge, once again, because it is still magnesium, it has to have the 12 protons. Otherwise, it would no longer be magnesium. So once again, it's electrons that are changed here, and it will have 10 electrons, which are negative charged. And that's going to leave you a +2 left over when you take 12 positive things and add 10 negative things. And once again, that is where our charge comes from. Again, the plus here tells us it has lost electrons. The +2 charge, the 2 part of it, tells us it has lost 2 electrons from the neutral atom. Any questions on that there? Aluminum, which is there on the bottom, is basically the same deal. Aluminum, if you look at the periodic table, should be 13. And once again, a neutral aluminum atom would have 13 protons and 13 electrons to balance it out to give you 0 charge, which is what we see here. Aluminum typically forms a +3 charge. And at that point, we would have still our 13 protons because it's still aluminum, our 10 electrons, giving us that +3 left over for the charge. So in all these cases, these are all cations with a positive charge, and that is a result of losing electrons. Typically speaking, the elements that make positive charges are metals. So metals typically will get rid of their electrons and become positive charges. So typically your cations are metals, or basically the ones are the elements that typically will do that. Any questions on that there? Now, if we wanted to sort of name a cation, and we're going to get into official naming chapter a little later on, but just so you have an idea, if you have any positive ion, be it sodium here, be it lithium, be it calcium, any of these positive ions, if we were going to name them, it's pretty simple. We actually just use the whole name of the element. So this would be known as the sodium ion. This would be known as the lithium ion. And that would be known as the calcium ion. So if you have to name just a positive cation by itself, you basically just use the whole name. If you had H plus, it would be the hydrogen ion. Now, it does get a little bit different if it is a transition metal, and we'll talk more about it in the naming chapter, but if it is a transition metal, except silver, cadmium, or zinc, we actually will include a Roman numeral with the name of the ion. So if you had iron, which is iron 3, this would be called the iron Roman numeral 3 ion. The 3 is for the charge. So we'll talk more about it when we get into the naming of official chapter. But transition metals, one of the characteristics of transition metals is they could actually have more than one charge. And because they could have more than one charge, when we typically name those type of ions or even just use them in a naming process, we do have to include a Roman numeral to indicate the charge. We don't have to do that for something like sodium, lithium, or calcium because they only make one type of charge. So it will never make any other charge, so you don't have to worry about the Roman numeral. You will never find a sodium with a +2 charge. It will always be a +1 charge. So since those charges are sort of locked in and fixed, we don't have to worry about Roman numerals. But if you had something like iron, it could be iron 3, and in certain cases, it could also be iron with a +2 charge, and that would be the iron 2 ion. So again, that's just a slight difference we use in naming cations that come from transition metals. The only ones you don't have to worry about that is like zinc, silver, and cadmium. And really, just to the right as well, if you look over there on the periodic table, things like lead, tin, antimony, in that sort of area, also need those Roman numerals as well when you name them. Any questions on that there? All right. So, get rid of that there, I think. Now, anions, as I mentioned before, are negatively charged ions, and they are a result of gaining electrons. So if we take a look at chlorine on the periodic table, that's number 17. So in a neutral chlorine atom, it should have 17 protons, as that is its atomic number. Because it has no charge, once again, it's got to have 17 electrons, which once again gives it that no charge. Now, chlorine will typically make a -1 charge. Once again, it has to have still the 17 protons, otherwise it will no longer be chlorine. But in this case, it actually will have 18 electrons. 17 positive things plus 18 negative things leaves you a -1 left over. And once again, that is where the charge comes from. In comparison of the neutral chlorine to the one that has the negative charge, we've actually gained electrons. So when you see a negative charge on an ion, it means it has gained electrons from the neutral atom, and the number of the charge will tell you how many electrons. So here a -1 charge means it's gained 1 electron from its neutral atom in this particular case. Same thing if we did something like oxygen. And oxygen, which is number 8 on the periodic table, tells us that in a neutral oxygen atom, we should have 8 protons and a matching number of electrons to give us that no charge. Oxygen will form a -2 charge, and that means that it still has 8 protons, otherwise it would no longer be oxygen. It would then gain a couple of electrons and end up with 10 electrons. 8 positive things and 10 negative things gives us a -2 left over, which once again is where the charge comes from. It has gained 2 electrons from its neutral atom, and that's what the -2 on the charge means. Minus it gained, 2 is it gained 2 electrons from its neutral atom. Any questions on that there? Now, in terms of representing this in an equation, you could actually do this this way. Since chlorine is a diatomic molecule, it actually will come as Cl2. Each individual chlorine will gain 1 electron, which means 2 electrons total, and that gives us 2Cl minuses. It is the electrons on the reactant side of the equation, and that indicates that those electrons are being gained by that particular element. Any questions on that there? When we name negatively charged ions, they are typically, by the way, nonmetals. So nonmetals are typically the ones that will form negatively charged ions. We do name it a little bit different. We take kind of the beginning part of the element name and we drop the last part of the name. Sometimes we drop a little bit more than the last part of the name, and we replace it with IDE. So Cl minus, instead of being chlorine, drop the last part, is the chloride, IDE, ion. Oxygen with a -2 charge, we drop a little bit more than the last part of oxygen, and we replace it with IDE. This is known as the oxide ion. So we call that. By the way, hydrogen, which is a nonmetal, is one of the only elements that can go both ways. We saw it earlier as positively charged. In certain cases, hydrogen can be negatively charged as well, and you would have something like H minus, which would be the hydride ion. Yeah. And so we basically drop the last part there and put it together with the IDE at the end. So if you see a name that ends in IDE, it most likely is a negatively charged thing, especially if it's an ion. Any questions on that there? Okay. So as we talked about here, as we talked about, I think previously as well, once again, it is only the electrons that change when something gets a charge. We do never change the protons, otherwise we change the element. Now, when we look at the periodic table, I'll do it here, I think, maybe. There we go. If we look at the periodic table, there are certain things on the periodic table that do have fixed charges. And everybody in group number 1 will form pretty much a +1 charge. Everybody in group number 2 will form a +2 charge. Skipping our transition metals, and honestly, pretty much aluminum is who we're talking about here, will form a +3 charge. We actually skip group 4. There's no good pattern, and that is because right around group 4, you got kind of that staircase coming down of those metalloids that are there. Above the staircase where the metalloids are nonmetals. So starting in group 5, when we look at the nonmetals present, above the staircase, -3. Group 6, nonmetals above the staircase, -2. Group 7, nonmetals above the staircase, -1. So we kind of go +1, +2, even though it looked like a 3, but that is a 2. +1, +2. We skip, go to +3. We skip 4 and go backwards, basically -3, -2, and -1. So these are the fixed charges that you see on the periodic table. As we just talked about a second ago, transition metals have a variable charge, which means just like we saw with the iron, in certain cases it could be iron 2 or iron 3. Copper, for example, could be +1 or +2 depending on the situation. There are 3 transition metals that, although they are transition metals, will still have a fixed positive charge. I'll put them here. It's not obviously accurate the way I drew my periodic table, but right around here we got zinc, cadmium, hang a left over there to silver. So these 3 transition metals will have fixed charges. Zinc and cadmium will make a +2 charge always, and silver will be +1. So those are kind of the 3 exceptions for the transition metal that have fixed charges. Again, pretty much everybody else in that transition metal region and below here, as I was talking about earlier, down there to the right is where you could find things like lead, which is Pb, tin, which is Sn. Those have variable charges, and it does depend on the situation as to what charge you will have for those guys. And those are the guys, as we'll talk about officially in the naming chapter, where we use Roman numerals. Once again, we don't use Roman numerals on things like sodium and potassium because they're group 1. They will always have a fixed positive charge. Like I said earlier, you'll never find a sodium with like a +3 charge. It will only be +1 no matter what the situation is because it is fixed. Any questions on that there? Now, it is also really important to remember that things do not have charges when they are by themselves. So if you have anybody from the periodic table by themselves, uncombined with any other element, they will not have a charge. So if you just have sodium metal, does not have a charge. You have potassium metal, doesn't have a charge. Things only get charges, as we'll talk about for sure when we get into the bonding chapter and also the naming chapter. Things really only get charges when they come together with something else. More specifically, when a metal on this side of the periodic table comes together typically with a non-metal on the other side of the periodic table, that is when these things gain charges. And they make, as we'll talk about, what's known as an ionic compound. They'll basically be held together by opposite attraction of the charges, positive charge attracted to the negative charge. That's what holds together an ionic compound. Actually, no sharing of electrons happening in that situation. Any questions on that? All right, so here you go. Again, your book will have these two guys, but usually for group 3, it really is our aluminum we're looking at. So once again, +1, +2, +3. We skip -3, -2, -1. Here's our zinc, cadmium, and silver. +2 for the zinc and cadmium, and +1 there for our silver in that case. Let's talk a little bit about the electrical nature when we do have ions. So when ions are present, they actually can conduct electricity, and solutions that can conduct electricity because of the presence of ions, positively charged guys, negatively charged guys floating around. These are known as electrolytes. So electrolytes are basically solutions that will break apart into ions, or substances that will break apart into ions in solution. And because the ions are present, helps kind of complete the circuit and conduct electricity really well in most cases. So there are a few different types of electrolytes. There are strong electrolytes. Strong electrolytes 100% break apart into ions. So for example, if you had a sodium chloride solution, and by the way, the AQ here means aqueous, is basically a water environment. It's basically a solution, which is a homogeneous mixture. What you actually have in solution is this thing will not stay together. It will 100% break apart into sodium ions and chloride ions. 100%. So if you had a beaker of sodium chloride solution, all you have floating around in there are sodium ions and chloride ions. You have absolutely none of these guys still together. Just going to completely fall apart into the ions in solution. Because it creates a lot of ions, it is a very good conductor of electricity. So if you had like a light bulb that you hooked up with some electrodes and you put it into a strong electrolyte solution, the light bulb would be very bright. Yeah, it would turn on and be very, very bright. It would conduct electricity super well. Now, there's also weak electrolytes. And weak electrolytes actually mainly stay together, but break apart a little bit. And a lot of weak electrolytes are weak acids, like this is hydrofluoric acid. And hydrofluoric acid, when you have a solution of hydrofluoric acid, will break apart into H plus and fluoride. You will have a little of these guys there. You will mainly have the whole thing still together. So if you looked at like a beaker of hydrofluoric acid, what you would see in that beaker is mainly HF units together still, but there would be a little bit of H plus and a little bit of fluoride ions floating around in the solution. Now, because there's still a little bit of those ions in the solution, they are able to still conduct electricity. So you're able to still conduct electricity. Not as well as a strong electrolyte. So if you kind of use the light bulb example and you had some electrodes on it and you stuck it into a hydrofluoric acid solution or a weak electrolyte solution, it would turn on, but it would look very dim, almost like it's dying, but it'll still kind of power up a little bit, but it wouldn't be definitely as bright as, say, the light bulb in our strong electrolyte solution. So it's still able to conduct electricity. One of the main differences that you see when you look at these equations, how they're written, that is a one-way arrow. Typically, weak electrolytes have two arrows, one heading in both directions. And because it has these arrows heading in both directions, this represents a reversible reaction. There is going from reactants to products, what's known as the forward direction of that reaction. But what is different in this type of reaction is as the reaction goes from reactants to products and you start to actually make some products, those products on the other side of the arrow will decide we want to come back together and go back the other way. So as you build up some products, the reverse reaction will happen. Those products will go back the other way, and that is what is known as the reverse direction of that reaction. It will continue on until it reaches what is known as chemical equilibrium, which is the rate of the forward direction will equal the rate of the reverse direction, and that is what's known as equilibrium. That is also what is known as Chem 1B. The entire semester talking about equilibrium is pretty much where you'll see those type of reactions a lot. But a lot of weak acids, a lot of weak bases are typically weak electrolytes. They mainly stay together, but do break apart a little bit. The last type of electrolyte is a non-electrolyte. And a non-electrolyte will dissolve, but no ions are formed. And for example, if you take a look at sugar, you could dissolve that in some water and you could get the sugar obviously to dissolve into solution. And sugar is a non-metal type of situation and it will not break apart. So basically all you get are whole sugar molecules in that solution. You actually get no ions. And because there's no ions present, it will not conduct electricity in this case because there's no ions that are present. So because you get no ions, does not conduct electricity. Again, it's those presence of ions which are really important for something to be able to conduct electricity. Any questions on the differences there? Is pure water a good conductor of electricity? Pure water is actually a terrible conductor of electricity because it's H2O, which is held together by sharing of electrons. There's no ions in it. Clearly, as a safety note, the water that comes out of your pipes is not pure water, right? So you will get electrocuted if you play with something in water. They actually, for example, in water, put a lot of ions in to clean it, right, and kind of sanitize it and all that. So water that comes out of your pipes, like your shower and your faucets and all that, actually has ions in it, which makes it a good conductor of electricity because it actually has ions present. But technically speaking, if you have pure water, nothing else present, because there's no ions in that, it's not bad conductor of electricity. Once again, safety note, don't blow dry your hair in the shower because you will get electrocuted, yes. Any questions on that? Okay. So here's that example of kind of the light bulb example. And once again, on the right-hand side, we have salt in this water, and that salt's going to provide those positive and negative ions being present, going to 100% break apart, going to turn that light bulb on very, very brightly. Once again, this pure water with nothing in it has no ions present. Once again, water is actually held together by what is known as covalent bonding. Unit of water does not break apart into ions or anything like that and lets you run an electrical current over it, and you'll still get hydrogen gas and oxygen gas and really not too much ions. And because there's no ions present, light bulb does not turn on, does not conduct electricity. Now, when we take a metal and a nonmetal, as I mentioned before, anything on the periodic table does not have a charge. It is only really what happens when a metal and a nonmetal get together that they do form charges, and the result of that is they form ionic compounds. So for example, if you took a sodium metal, it has 11 electrons, and it has one electron, I'll just represent like so. This is what is known as a valence electron. And a valence electron is the outermost electron. It is the one that is actually furthest away from the nucleus. So if you remember when we talked about the atom, there's an attraction between the electrons, which are negatively charged, and the nucleus, which is positively charged. But the valence electrons are the ones very, very far away from each other and are far away from the nucleus. And it's the highest energy ones. And those are actually the ones that are involved in bonding. So for sodium, it actually has one valence electron. If it hooks up with chlorine, which has a total of 17 electrons, and chlorine actually has 7 valence electrons. So chlorine has 7 high energy electrons on the outside. What happens in this for various reasons that we will talk about in later chapters is chlorine has some attributes that makes it want to basically collect as many electrons as it can. So it wants to, I don't want to say as it can, but it has the ability to bring electrons towards itself. It's probably a better way of wording that. And what happens when sodium and chlorine get near each other is sodium is like, I don't really care. If you want my electron, you could have it, right? So it's not going to put up much of a fight. And what ends up happening is the sodium will send an electron over to the chlorine. So if chlorine wants the electron, the sodium's like, I could care less, you could have it. And the sodium will give up its electron. The result of sodium giving up its electron is it will now have one less electron, right? And now end up with 10 electrons. And it's at that point, it will end up with a +1 charge and only 10 electrons from its 11 it started with. Now the chlorine, as you can see, will actually end up with that electron, and I'll circle it here, that electron that came from the sodium in this case, and it will actually end up with a -1 charge because it now has one more electron than it started with. So instead of 17 electrons, it now has 18 electrons in this case. And that is how an ionic compound forms, and that is what's known as an ionic compound. The sodium chloride is an ionic compound, sodium being the metal, chlorine being the nonmetal in this particular case. There is, as we will talk about in more depth when we get to that chapter, absolutely, positively no sharing of electrons happening here. So what is holding that together is the attraction of the positive charge of the sodium and the negative charge of the chlorine. That is what is kind of sticking those guys together. In that case, there's actually no sharing of electrons here. By the way, as a side note, preview of what we will talk about, when I look at where these guys end up in terms of electrons, the sodium ends up with 10 electrons. Who on the periodic table has 10 electrons? In their neutral state, who should have 10 electrons in a neutral state? Neon, right? And the chlorine ends up with 18 electrons. Who has 18 electrons in its neutral state? Argon, or the AR underneath it, yeah. Both neon and argon are what group on the periodic table? They are group number 8. Those are the noble gases. So if you remember, as we talked about, noble gases are chemically inert. They are super stable. The whole basis of bonding, this type of bonding, which is ionic bonding, covalent bonding, is for everybody to end up with the same electrons numbers as people in group 8. And they want to end up with 8 electrons or have a similar electron configuration as those in group number 8 because they're really, really stable. So that really is the goal of bonding. This particular type of bonding is achieved because if you look at the location of sodium on the periodic table, it's able to get to that noble gas configuration by losing electrons. It backs up one spot to neon's configuration by losing that electron. It goes from 11 to 10 and backs up back there to neon. If you look at chlorine, it actually goes forward on the periodic table by gaining that electron, and it ends up in that noble gas configuration. So what happens in an ionic compound is both elements are able to achieve that really stable electron configuration by gaining and losing electrons, and that's also what allows that attraction and that compound to stay together, is because everybody's now in a super stable sort of situation. And that really is the goal of everybody in bonding, is to end up same electrons as group 8. Any questions on that? By the way, does sodium become neon, and does chlorine become argon? Do they change elements? They do not, because sodium still has 11 protons, and chlorine still has 17 electrons. So what we're talking about here is they become similar to the noble gases in terms of their electrons, but they still remain the same elements. Any questions? By the way, what we see here is what an ionic compound looks like in the solid state. They come together to maximize the positive and negative attraction between the ions and minimize the repulsion attraction of positives near positives and negatives near negatives. Why is the chloride atom larger than the sodium ion? When somebody gains electrons, their size gets larger, right? So between neutral chlorine and chlorine with a -1 charge is the chlorine with a -1 charge, or chloride, has gained electrons. Their electron cloud gets bigger, right, because they have now more electrons. So the size of a negative ion versus its neutral counterpart should be larger. When we look at the sodium, sodium loses electrons. So from the neutral sodium to the one that lost electron, its electron cloud shrinks because it gave away its electrons. So a positive ion typically is smaller than the neutral atom because it lost some of that electron cloud by giving away electrons. Any questions on that there? Right. Now, one last thing as sort of a preview. When we do make ionic compounds, whenever you take a positive ion and you put it together with a negative ion, it has to equal 0, the overall charge. It has to equal 0 in the simplest way possible for it to get that charge of 0. So if we take a sodium ion and we put it together with a chloride ion, +1 and -1 is 0, which means the formula for sodium chloride is NaCl, sodium being the whole name of the metal, IDE for the negative ion, which is chloride. Now, when we do write a formula for an ionic compound, it should never have a charge. So when you take a positive guy and a negative guy and actually put them together like I did in the box, it should not have a charge. But you should remember that because it's an ionic compound, it actually is made up of two things that do have charges. So it actually is made up of two things that do have charges, but should not have an overall charge. If you took the calcium like you see there, which is +2, and the chloride, which is -1, if you were to just put them together exactly 1-to-1 here, you would end up with CaCl, and when you take +2 and -1, you would actually end up with a +1 charge. And that is a no-no when you put those guys together. It has to equal 0. So in this case, I don't need one chloride, but I actually need two of them. And I would have a formula CaCl2. One calcium, one and two chlorides. Remember, the subscript goes to the element to the left, right? So if nothing is written there, it represents 1. And obviously the 2 represents there. And that would be the proper formula for calcium chloride. Again, just putting those two names together, calcium, whole name of the positive guy, and chloride, the name of the negative ion. So if we take a look at this, that is barium, which is a +2 charge, oxide, which is a -2 charge. If I put those together, +2 and -2 equals 0 when you add them together. That means I just need one of each of those guys, and that would be our proper formula. Again, has no charge when we put it together, but is still made up of a cation that is +2 and an anion that is -2 in charge. If I take aluminum ion and want to put it together with the sulfide ion, in this case, the common number between 3 and 2 is 6, right? So I need to get each of these to 6. You get that common number by just multiplying them together, right? 3 times 2 is 6. So to get aluminum to 6, I don't need 1, but I actually need 2. That's going to give me a +6 charge overall. To get the sulfide to 6, I need not 1, not 2, but I need 3 of those. Each one is -2, gives me a -6 to balance out the +6 that I have there. Now my formula is this. Aluminum, I have how many? 1 and 2, so that is 2. Sulfide, I have 1, 2, and 3, S3. And that would be, again, the proper way to write it without the arrows. 2 aluminums and 3 sulfide. Overall charge, 0. The purpose for this is we'll talk about more when we get to the sort of the bonding chapter, but essentially that allows everybody there to reach that noble gas configuration, everybody to get to that group 8 sort of electron configuration by doing that. This would be known as aluminum sulfide in this case. Question on that there. Now, sometimes people are taught this, which is, well, all you have to do is just move this down there and that number down there, and you get Al2S3. And you can get the formula just by doing that. Or if you have the numbers on the bottom, you could just move them up to get the charges. And that does work about 92% of the time. It does not work 100% of the time. So if you're good with 92%, you could just kind of blindly do that. But you will miss a number of them that it will not work out right for you. So it's better to kind of think about just balancing out the charge to 0 and how many of each that you need to get it to 0. You'll always get the right answer. Any questions? All right. And that is chapter 4. We are then going to go actually to chapter 11, I think is next. Okay, so in this chapter, we're going to talk about a few things, but mainly we're going to talk about electrons and what's happening with electrons as they transition from one energy level to the next. We'll also talk about electron configuration and how to write that in this chapter. So one of the ideas here is essentially this idea of electrons transitioning from one energy level to the next, and what happens in terms of how that occurs. So Rutherford basically described the atom as having this positive core nucleus. We have these negatively charged electrons moving around. The nucleus is really small compared to the size of the atom, and the electrons make up all that empty space. So one of the main sort of things we're going to be talking about in this chapter is if we have an atom that has electrons, say represented with these arrows on a, actually I'll just represent it with one arrow, but either one, we'll just get rid of that one. And let's just say that this is a lower energy level, and there are some higher energy levels. And when you have an atom and you do something to it, for example, like we're going to do maybe next week in lab, a little flame test action, and you put that atom into flame, or you run an electrical current through it if it's in the gas phase, what that's going to do is create a lot of energy that the atom's going to absorb. It's going to be kind of endothermic for the atom. It's going to absorb all that energy. The result of that is you're going to basically excite electrons from a lower energy level to a higher energy level. So when you do that, this electron gets excited, and it maybe goes all the way up. We'll just go all the way to the top here. And this electron ends up at a higher energy level. Now, one of the things that's important in chemistry is things tend to not want to be in high energy. High energy is usually a very unstable position in chemistry. A lot of what happens in chemistry is all for the sake of trying to lower the overall energy, getting things down to a lower state of energy. So what's going to eventually happen with this electron that you just shot up to a higher energy level is it's going to try to work its way back down to a lower energy level. So this electron that's up there on top will find itself coming back down to a lower energy level. Maybe it comes all the way back to the bottom, maybe it doesn't. But there is what is known right as the law of conservation of energy, which says energy cannot be destroyed or created. So in order for the electron to drop back down to a lower energy level, the atom itself will have to give off that energy as a form of a photon of light. So what will happen is the atom will give off that energy to allow that electron to come out, and it will become a photon of light. And depending on the wavelength, for example, of that energy that's given off by the atom, it may be something that we can visibly see. So for example, when you do a flame test and this occurs, you see the flame color change from no color to like maybe green or maybe red or blue or something like that. You maybe have done a flame test yourself without knowing it. If you ever boiled water and it overboiled and hit the flame of your stove, or that may be a fire if you have a fire stove, this flame on the stove will change color, or go kind of yellow real quick and kind of go back to maybe a bluish type color. And that is because basically you have sodium or salt in your water, and that is the sodium ions, electrons basically going to a higher energy level and coming back down, and we see that. So if that energy falls in the visible part of the spectrum where we see color, like that Roy G. Biv, right? Red, orange, yellow, green, blue, indigo, violet, we will see some type of color. By the way, that is also what is happening with fireworks, right? When you shoot off fireworks, they explode, a lot of energy to the elements within the fireworks. As those electrons start relaxing back down, we see all the pretty colors that come out, right, in the fireworks, basically, and all the different colors that occur. Any questions on that? So this sort of interaction is really the basis of what we're going to talk about sort of in this chapter, and we're talking about some calculations involving, the energy that comes off. So sort of the earliest work that was done in sort of this arrangement or area was done by a guy named Planck. And he did a lot of work by heating solids to different temperatures. And what he noticed was when energy was released, it was released in these sort of packets of energy, this discrete sort of packets of energy, which is known as a quanta of energy or a quantum of energy. And a quantum of energy or quantum of energy is this idea of we will give off a certain amount of energy every time. It's this sort of known amount of energy to do that. And really what it means, as we will talk about in context to our electron, if you will, is if I have an electron here on this energy level and it wants to get down to a lower energy level, it will be able to release enough energy to basically make it all the way from that top energy level to the bottom energy level without stopping along the way. You could think of a quanta of energy, as we will see maybe some examples a little later on as well, as like a staircase example. And the idea there is if you're walking stairs, you have enough energy to make it to this step, right? Or this step, or this step. You never, right, when you're walking stairs, go, I'm just going to take a break between steps, right? Because you're going to fall, right, and not be there. And that's the same idea as how things like electrons move from different energy levels. They will gain enough energy to go from this energy level to the next or wherever they need to go. They will lose energy to go from a higher energy level to a lower energy level. They will never just kind of park themselves in between energy levels. So they will either gain enough energy or lose enough energy to fully make the transition from one energy level to a next. And that's sort of the idea of quantized energy, is that they basically can make the full transition. They will not stop anywhere there. As we'll talk about later on, there's what is known as continuous energy, which means you can pretty much stop anywhere you want along the way. But electrons basically move more in this quantized fashion. One of the earliest developments in sort of Planck's quantum theory was the idea of radiation. And radiation is really the emission and transmission of energy in space in the form of waves. So as somebody is gaining energy, as somebody is losing energy, it is basically being given off in the form of a wave through space. So a wave basically transferring that energy through space. So let's talk a little bit about some properties of waves. A wave can be thought as a disturbing vibrance of energy. So as you can see, our little bird there in the ocean, he's actually staying, and the wave is basically passing him, right? And as you maybe know, if you've ever been in the ocean, some waves are not too bad, right? But there are some waves that carry a pretty good amount of energy as they pound you into the water, right? And stuff like that. And that is how energy sort of moves through space in the form of waves. So when that atom, for example, in my example I just put up there, when that electron goes to a lower energy level, that atom's going to give off that energy in the form of a wave. Again, a wave will have certain characteristics and certain energy associated with it as well. So not all waves are the same. Depending on the wavelength, can have more or less energy associated with it. So let's talk a little bit about those characteristics of waves. So first off, a wavelength is lambda. So if we take a look at a wave, lambda is the distance between two peaks or even two troughs is the wavelength. And it is typically expressed in units of meters, centimeters, or nanometers. Nano is used a lot, especially because the visible part of the spectrum is usually given in nanometers. A reminder that nano is 10 to the minus 9, yeah? So in 1 nanometer, there are 10 to the minus 9 meters. So that's a conversion that's used a lot. Again, because the visible part of the spectrum where we see color is typically given in nanometers. Centi, obviously 100 centimeters in a meter, and obviously meters are common units. Frequency is another very common characteristic. Frequency of a wave is the number of waves that pass through a particular point in a second. It is oftentimes called by people the little V symbol, but it's really not a V. It's kind of a nu is what this symbol is. It kind of looks like a funky V, but it's actually nu. And usually frequency is measured in reciprocal seconds. which is 1/seconds, or it is also a hertz. So a hertz, 1 hertz is the same as a reciprocal second. And that's the frequency, right? So for example, when you tune your radio to 95.5 megahertz, right? That is the frequency of that radio station, right? Sending out those radio waves to your car. And that is in megahertz, is sometimes how radio waves and frequency is sometimes given, mega being 10 to the sixth in this case. Amplitude is the distance from the midline to the peak. So this would be the amplitude of the wave. And the speed of the wave can be found by taking the product of the wavelength times the frequency. So typically this is sometimes referred to as the speed of the wave. Wavelength is meters times the frequency, which is 1/seconds. So typically meters per second are the typical units that we use for how fast a wave is moving. Is the typical units that we use. Meters per second is typically the units that we do there. Any questions on that there? Now, as I mentioned before, when electrons transition, it may give off a wave that has a wavelength in that visible part of the spectrum where we actually see color. But there can be electrons that transition outside of the visible part of the spectrum. It could be something like in the infrared part of the spectrum where we feel heat. So it doesn't always result in, say, a color that you see as electrons transition. But if it does transition in sort of the visible part of the spectrum, that is typically where we do see colors. Now, light behaves like electromagnetic radiation, which again is that emission of energy in the form of these electromagnetic waves. And electromagnetic radiation can sometimes have properties that are similar to particles, and particles could also have wave-like function as well. So there's kind of a dual nature of light. As we will talk a little bit about, we're not going to go into extreme detail for a lot of this, but the idea here is light can behave like waves, but can also have particle-like function. And particles like electrons can obviously behave like particles, but can have some functions that are very similar to wave-like functions. So there's a sort of dual nature of light, and they have different properties. So one could think of a beam of light traveling through space as a stream of tiny packets of energy, which are called photons. There is a relationship between the wavelength and the energy of that wave. So if you have a longer wavelength, we got this longer wavelength. Typically a longer wavelength usually means a lower frequency and usually means lower energy. So the longer the wavelength, the lower the frequency, and the lower the energy. If you have a shorter wavelength, it just keeps going. The shorter the wavelength, the higher the frequency, and usually the higher the energy associated with it as well. For example, we talked just a second ago about, we talked about radio waves. Radio waves are longer waves. They have lower energy, which is why it's not too dangerous to sit and listen to your radio in your car, but it has a lower energy. Something like X-rays, as we will see, has a much shorter wavelength, a much higher energy. Why they throw you a lead vest and relieve the room when they shoot an X-ray at you, right? So it's very, very high in energy. Radioactive sort of particles like gamma rays are very, very high in energy as well. It's very short wavelengths. So here is the idea, again, light as a wave. It will have some wave type function and also can be a stream of particles or this packet of energy that occurs. And here's again, as you can see here, even between colors, red versus blue. Red actually has the longest wavelength of the colors, and is actually lower in energy than when you get closer to kind of the purple bluish area. That has a much shorter wavelength, a much higher in energy uh, than your red counterpart. So, for example, you could even make a prediction if you were doing something like a electron discharge tube, or you observe maybe a red light come out as something is happening versus a blue light. You can make an assumption that perhaps the electron is not transitioning as much energy as, say, bless you, the blue one. So, for example, maybe this is a result of an electron just transferring one energy level, which would be not a lot of energy and have a longer wavelength, as opposed to maybe for our blue, maybe it's transitioning a bunch of energy levels, a lot more energy transition, giving off a lot more energy and a lower wavelength that occurs as well. Now, a feature common to all electromagnetic waves is basically the speed at which they travel. They travel at 2.9979 times 10 to the 8. That is the number they want you to learn here. Most people will roll with 3 times 10 to the 8, but here they would like you to roll with 2.9979 times 10 to the 8 meters per second. That is what is known as the speed of light, which is c. So c is the speed of light. You need to know, obviously, that number, 2.9979 times 10 to the 8. And that gives us a formula that is used. The speed of light is equal to the wavelength times the frequency. This is in meters per second. This is meters the wavelength has to be in, and reciprocal seconds is what the frequency has to be in. So if you want to know what the wavelength is, and you know the frequency, the wavelength will be the speed of light divided by the frequency, so you could calculate it. If you want to know the frequency and you know the wavelength, the frequency will be the speed of light divided by the wavelength. So you can use this equation when you're dealing with electromagnetic radiation to figure out the wavelength or the frequency if you know the other. Again, C is a constant, and it's that 2.9979 number times 10 to the 8. So obviously you should know these here. All right, let's try one more here. What is the frequency for a wave with a wavelength of 4.68 times 10 to the minus 7 meters? Since we're getting to the end, let's take a look at it together here. So once again, we can use our formula. C is equal to the wavelength times the frequency. We're looking for the frequency. We have the wavelength given to us, which is in meters, so 4.68 times 10 to the minus 7 meters. And once again, that is the proper unit that we need. Once again, our speed of light, which again is that constant number that we saw over here, 2.9979 times 10 to the 8 meters per second. So rearranging this, we're just going to divide that to the other side. Gives us the frequency is c divided by the wavelength. So we'll take 2.9979 times 10 to the 8 meters per second divided by 4.68 times 10 to the minus 7 meters. Those will cancel. When we divide this, the reciprocal seconds will be there, and we will end up with 2.9979 to the 8. Make sure you use your exponent button. 4.68 to the negative 7. Going to give us here a frequency of 6.41 times 10 to the 14. The units here are reciprocal seconds, which you could write like that, or you could write the units as 1 over seconds, which, by the way, is the same thing as a hertz. Any questions on that calculation? All right, we're going to lay it up there for today.